So formative assessment 6. And here we have question 1. A point mass is moving on a horizontal circle with a velocity of constant magnitude v. At one particular time, the mass is at P, here. A short time later, it's at Q, here. Which vector diagram correctly shows the change in velocity of the mass during this time? So the first thing to do is to find that change in velocity, which you might already remember is towards the centre. So you should get a vector that looks like this. But let's do the proof ourselves. We're going to do v minus u over t. That will give us acceleration. This is v, this is u. So we need to subtract minus u from v. So as a vector diagram that looks like this, we have the v vector plus the minus u vector, which is this one. So we're going to add that by drawing it nose to tail. So it looks approximately, the resultant force looks approximately like this. Bing, that's your resultant. Okay, now you are not going to find a triangle like that as your options, because this is a bit of a trick question. What you have to look for in the answers is not the entire triangle, but just the resultant. So the resultant here, the change in velocity, is going in completely the wrong direction. This one is even more wrong, if that was possible. But if we look at C, it's the right vector, even though this arrangement doesn't match up with what you did here. Okay, but that doesn't matter, because the question isn't about the whole combination of forces. The question is only about the change in V. So this one matches your resultant. So the answer is C. So two satellites of equal mass, S1 and S2, orbit at a distance r from the Earth's centre at speed v. S2 orbits at distance 2r from the Earth's centre at speed v over square root 2. The ratio of the centripetal force on S1 to the centripetal force on S2 is one of these. So let's have a look. We know that this has everything to do with velocity and force. So the relationship that brings those two together is F equals mv squared over r. So we want to know the ratio. The ratio of the centripetal force on S1, so that would be F on S1 over the force on S2. Now the force on S1 over the force on S2 will be equal to mv squared r1 over mv squared r2, and by that would be m1 and m2. And this would be v2 and v1. Okay, so now we need to start substituting the values that we're given. On S1 it's r, on S2 it's 2r. The speed in S1 would be v, and for S2 it would be v2. So let's substitute those values in. Okay, so these are our values here. We have mv squared over r over mv squared over r, but our v is v root 2 and our r is 2r. Okay, so if we simplify this section here, squaring out the root 2, okay, now you can see our extra quantities. Now all of these will cancel out. mv squared r, we can get rid of those and we'll be left with our answer, which would be the ratio. So let me just cancel out all of these. Okay, and you're left with 1 over a half divided by 2. So you can multiply these two out. Okay, so you get 1 over 4, which from just straightforward maths, this would be equal to 4. okay? Because if you divide a number by a fraction, then you can rearrange it in this way. The denominator goes up to the top, like that. Okay? So there, your answer is 4, which is C. Okay, so in this one, if the radius Rm is from the moon to the Earth, and the distance Rs is from the sun to the Earth, okay, how do we work out the ratio of gravitational field strength due to the moon and the gravitational field strength due to the sun? So the Earth is here, there's the sun. This is obviously not to scale, okay, so there is our Rm and our Rs. Okay, so let's have a look at the G for the first one, that the Earth feels due to the moon. Okay, so that would just be G, M of the moon, divided by radius. Well, that, call it, it's not radius. Well, it is a radius of orbit, but it's just call it a distance. There we go, squared. And now that would be divided by, because we want to know the ratio of the gravitational field strength of the Earth due to the sun. So we'll call that GM, and we'll call this one GS. And now that would be GM, oops, that would be the S, mass of the sun, R, distance to the sun, squared. Okay, so let's just isolate what's happening here with the radii, because there is a proportionality. This is definitely proportional to some radius-based relationship. We just need to have a look at it. So let's isolate just the radiuses. We can see we've got 1 over distance to the moon squared divided by 1 over distance to the sun squared. Now, because you're dividing a fraction by a fraction, you have to kind of rearrange everything. So the radius of the moon would slip to the bottom there. And because this one is 1 over Rs, then 1 over Rs would flip to the top there. So this would go on top. So you would end up with Rs over Rm squared. So the answer is C. Okay, this question is not in your syllabus. It's on the high level, so leave it for now. Number 5. The diagram below shows 2 planets, X and Y, of masses 2m and m, respectively. The centres of the 2 masses are separated by a distance of 2d. Point P is midway between planets X and Y. The mass of each planet may be assumed to be concentrated at its centre. Okay, so that's a given. The magnitude of the gravitational field strength. So this is a forces question. G, gravitational field strength, is a vector. So you're going to feel a pull in this direction thanks to 2m, and a pull this way thanks to m. And we would expect this one to be larger. So let's find out how big this force in this direction is. We have G equals Gm over R squared. But using the correct values, what we've got is G 2m. Okay, let me finish this off. Over d squared. Okay, so Gm over d squared, because if that whole distance is 2d, then that distance is just d. So that's the pull in this direction, thanks to this this mass, this big planet. So now we're going to look at what happens in this direction. Now it's opposing and it's a vector, so we now need to subtract it. So what we're left with is Gm, this time it's just mass on its own, over d squared. And that's just some really simple algebra left to do, because we've got 2 of these and 1 of these, and we're left with 1. Gm d squared, which is B. Okay, the acceleration of freefall of a small sphere of mass 5 times 10 to the minus 3 when close to the surface of Jupiter is 25 meters per second. The gravitational field strength at the surface, well, it's a trick question. It's actually the same. The answer is C, because force equals mass times acceleration. The acceleration due to a gravitational force is 25, but by definition, the gravitational field strength is equal to force over mass, which is what acceleration is equal to. So they are equivalent. So that's a trick question that may come up again. Okay, this is a straightforward one. A satellite of mass m and speed v orbits the Earth at a distance r from the centre of the Earth. The gravitational field strength due to the Earth at the satellite is equal to, well, G is equal to force over mass. Force would be equal to mv squared over r. Now, the m would be the mass of the object in the field. But when we talk about the definition of gravitational field strength, the mass is also equal to the object in the field. So, if we find G from this one, we have G equals F over M, which is equal to mv squared over r over m, and it's the same m, so we're left with v squared over r v. This is exactly the same as the previous question, but now using circular motion, because this, as you hopefully remember, is acceleration due to gravity. The acceleration towards the centre of an object that's moving in a circle. The gravitational field strength at a point, it may be defined as, and this is just definition question, the force per unit mass on a small mass placed in a point. Okay, and this, funny enough, is the answer to this question. Okay, so it's really, really worth learning these definitions off by heart. Okay, the diagram below shows 3 points above a planet. The arrow presents the gravitational field strength at point A. Draw arrows to represent the gravitational field strength at point B and C. Okay, now looks really easy, and it is, but you've got to be careful of a few things. C is at the same distance from the planet as A. So what you need to show is that the two arrows are the same size and that this one is pointing towards the centre. B is actually further away, so the arrow needs to be smaller. And it also needs to point towards the centre. Okay, so something like that. So the size is important. So this one should be the same as this one, and this one should be smaller. State Newton's law of gravitation. Okay, what's important you state is, first of all, the proportionality. Okay, it's proportional, that you state that it's proportional to the product of the two masses and inversely proportional to the distance squared. Okay, so 3 marks there. Proportional to the product of the masses, inversely proportional to the distance squared. In the second part, it's just a simple calculation question. The average distance of the Earth to the Sun is 1.5 times 10 to the 11. The gravitational field strength is 6 times 10 to the minus 3. Estimate the mass. So we're just going to use the field strength equals G, mass of the planet you're on, or of the one exerting the field, over r squared. Okay, so you substitute all your values into this relationship, and you should get the answer of 2 times 10 to the 30 kilograms. Okay, deduce that the orbital period t of a planet around the Sun is given by the expression t squared equals a constant r cubed, where r is the radius of the orbit and k is any constant value. Okay, so we're going to start with our force relationship. That on the one hand is equal to the product of the masses over the distance squared, but in circular motion is also equal to the mass times the velocity squared over r. And let's do some simplifying. Okay, so that gives us this expression. But on the other hand, from circular motion, we also know that the linear speed is equal to 2 pi r over t. So if we square that, we end up with 4 pi squared r squared over t squared. Okay, so if we substitute this now in to here, we should get, okay, so you get this substitution in there, and you should get this new equation. Now, let's rearrange it to put all of our radiuses on one side and period on the other. So we're going to bring that over up here, and we're going to take that over there. Okay, so you get this expression now, 4 pi squared r cubed equals gmt squared. And now we're going to pass this over to that side, because we're going to cancel these and go here. And what you can see is that all of these are constants. 4 is a constant, r squared is a constant, g is a constant, and m is a constant. And r is and t are proportional. Okay, and in fact, t is equal to constant, which is 4 pi squared over gm times r cubed, sorry. Okay, so this is a really common question. We have to derive an expression for gravitational field strength at the surface of a planet. So you actually have to derive this formula. And our starting point is Newton's law. Force equals g m over r squared. So that'd be 1 point. And then we need to think, okay, so the definition of gravitational field strength equals force per unit mass. So therefore, if we substitute this expression for force into here, we end up with G equals big G m times m over r squared over m. These cancel out, and you end up with your final expression here. This question here is very straightforward. It's using this relationship. Substitute your values for gravitational field strength in for G. Your radius, 7.1 times 10 to the 7. In here, your constant is 6.67 times 10 to the minus 11. And you rearrange to find m. Okay, and you should get a value of 1.9 times 10 to the 27. Okay, the question is about a satellite orbiting the Earth. A satellite S is in orbit around the Earth, and the distance r is 4.2 times 10 to the 7. And here you can see a visual representation of that. In the diagram above, draw arrows to represent the force acting on the satellite. Now this is a kind of trick question, because a lot of people do draw a force along the line that it's moving. Okay, there is only one force, and that's towards the centre of the Earth, and it's like that. This is a simple proof now. To deduce the velocity v of the satellite is given by v squared equals gm over r, where m is the mass of the Earth. So that's just going back to Newton's law, F equals gm over m over r squared. But bringing in, because we need to talk about velocity, circular motion, so equals mv squared over r. You cancel out the repetitions, so you get rid of that small m, and one of those r's, and you're left with gm over v squared. Okay, so this next one, hence deduce the period of orbit t is equal to this. This is exactly the same as the question I did a few pages ago. So where you had to prove that r cubed was proportional to r squared. Okay, so the same proof. Now we need this expression for the next page and the next question, which asks you to find t. You need to find the period. In the previous question, you're given t squared equals 4 pi squared r cubed over gm. Okay, so if you substitute your values in, let's look at what information we have. We have that gm over r squared is equal to 10. Now you've got the inverse, you've got gm over r cubed. So you could replace this with, all of this, take 1r, leave it there, and leave 1r here, and get rid of the squared. Okay, so what we're doing is we're turning this around. Gm over r squared equals 10. So r squared over gm equals 1 over 10. And we're putting that in here. Okay, so we're left with t squared equals 4 pi squared times 1 over 10 r. And we're going to substitute our value for r there. And you should end up with a time of approximately 24 hours. This question is about an atomic model. The diagram below shows a simple model of a hydrogen atom in which an electron orbits in a circular path. On the diagram, show the acceleration. Now this is a really common question. The acceleration is the same as the force in circular motion. The acceleration is always to the center. How do we draw the velocity? The velocity is at a tangent to the motion. So it's like that. So that would be v and that would be a. Now this takes us back to electric fields. State an expression for the magnitude of the electrostatic force. F equals k q1 q2 over r squared. But our charges are electrons, so we don't need to say, we don't need to leave it as q. We've got an electron and we've got a proton. But a proton has the same charge numerically, it just happens to be a different sign. So what we end up with is k e squared over r squared. Now this is a sneaky one. The orbital speed of the electron is 2.2 times 10 to the 6. So it's sneaky in that it's exactly the same as a circular motion question, but using electric field theory. We've got a speed, v squared. So that must have something to do with circular motion. Of course it does. It's moving in a circular motion. The force towards the center of an object moving in circular motion is mv squared over r. Okay, and that's equal to the attraction between the charges. So that would be equal to k e squared over r squared. Okay, so if we need to find the radius of orbit, we could rearrange these. Okay, if you rearrange it to make r the subject of the equation, here I've just cancelled the r's, the repeating r's. So r is equal to k e squared over mv squared. And if we substitute our values in, remember, we have the mass of an electron here because the electron's the one that's spinning round. The proton is in the centre. So the electron is the mass we're considering. And let's put our numbers in. Okay, so what have we got? We've got the constant of proportionality here, which is the Coulomb constant. That's on the data booklet. We've got the charge on an electron, or a proton, which is 1.6 times 10 to the minus 19 squared. You've got the mass of an electron, 9.1 times 10 to the minus 31, times 2.2 times 10 to the 6, which is the velocity squared. And you should get the radius of orbit, 5.2 times 10 to the minus 11.